Well, hi everybody. Thank you very much for coming. This is Exam Jam. So I don't know if you were down in the Sid Smith lobby, but they do have free snacks, free massages. This is one of the dogs. They have at least two dogs, and you can pick up the dog. There's coloring. There's just various fun things that you can do to try to get you in the spirit, I guess, of the whole exam schedule is coming up. So this is the official schedule. I think, like I say, it's gonna start at 9 a.m. on Saturday, December 16th. So that's a bit of an extra challenge, I think, is to get yourself there. I try to arrive at least by like quarter two or something, because they're going to start admitting people to sit down at 8:50. So I'll be around. There's 8 different rooms, so I'm going to be wandering around to the different rooms. But this, like I say, this split of last names is official, and it's linked on the SharePoint there. And there are a few students who've got something different listed on Acorn. So you'll have some students have been saying they're told one thing on Acorn and one thing on SharePoint. It doesn't really matter, actually, because it's just about this split. We have these 8 rooms, and you might be sent to a different room, so it's all physics. But Holland assures me that it's best to just follow the SharePoint. So there you go, this one, because that hasn't changed. It's just somebody typed the wrong thing on Acorn, I think, and it's causing a bit of confusion there. Okay. So, and the other thing is, absolutely feel free to let me know if you have any questions or anything. I got, my plan was basically, I'm gonna go through some examples, I guess, of things that I think have come up on past exams, and might show you sort of my thought process of how I've gone through some of these things. So this is exactly what you're gonna see when you sit down, the first page and a half. And also the instructions, I guess, just for the 2 parts. There's questions 1 through 11 is the multiple choice part. Then question 12 and 13, you have to write on these exactly the same kind of sheets that you had for the term test. And those are they get scanned in. There's a bubble sheet, and then there's 2 of these written problem parts. And then we collect those, April scans them into grade scope, and then the TAs mark it. And so that's the other thing, is that she probably won't have that scanning done until Monday, and then the university closes on Thursday, and there's a QP rule that I can't ask a TA to give a turnaround in less than 5 days. So your actual mark in Physics 131 won't come out till probably January 4th, January 5th, like that. Just because of that marking delay. So it's just warning there. But, we'll do a good job of it. Okay. So I've also posted this on the Quirkus in case you want to take a look. I think it's under that class 36 module. Okay, you want to do some examples? This is sort of a past exam thing, but this is a chapter 8 kind of static equilibrium problem. Where you need to do is, I guess, draw I call it the extended force diagram. How does that look? All right. So what you're kind of seeing is a little diagram of an actual mirror that's in my shower. And I don't know, it says 1 and 2, and people ask me what the little bump is on 1, but I'll tell you that in a minute. But so the extended force diagram, what I try to do is draw just a really rough sketch. So it actually looks like this, right? That's the object. And then you have forces that are acting on it. So, well, what is acting on it? So I guess there's the force of gravity. Draw mg acting down like that. And then you've got these forces here. And so I will just draw maybe, I don't know, like there's a surface there, right? So there's a normal force, we call it N1, and a normal force here we call N2. And then something I think has to be holding it up. So what we're going to have is the sum of all the forces in the x direction is equal to 0. So let's define y to be up and x to be towards the right. The sum of all the forces in the y direction have to equal 0, and the sum of all the torques have to equal 0. So 3 equations, 3 unknowns. So what I'm going to also list here is this force of static friction or something like that, N1, N2, and Fs. Because I think there has to be an upward force to cancel out gravity or the whole thing's going to fall. So I think it's a suction cup. Okay, so the sum of all the forces in the x direction is equal to N1 plus N2, I think, which equals 0. So that doesn't make any sense. Unless one of them's negative, I guess. So they have to both be 0 or something. So let's just say N1 equals negative N2. What I like to do with these problems is first do the easy equations, the sum of the x and sum of the y is equal to 0, and see if I can solve it. And if that's not working out, then I'll try the torques. But what this means, we're certainly going to need to use torques in a minute. But I would say if N1 equals N2, negative N2, then they're either opposite in direction or they could both be 0, I guess. These are either 0, I guess that would be okay, or in opposite direction. And now I'll show you the trick. Oh yeah, and then the other one is that the sum of all the forces in the y direction equals 0. That's going to be Fs minus mg. So Fs equals mg, that's okay. So what I'm going to do is let's define the axis to be up here. So then, if I do that, define it at the top. It's PA day today, so this is my son. Okay, then you've got the sum of the torques is going to be so they've even listed W there. This force line has a lever arm W from here to here, and the force should be pulling it clockwise, right? If you're rotating around that axis as I've drawn, and the torque due to gravity, it's going to be, let's call it the torque due to gravity plus the torque due to friction plus the torque due to 1 and the torque plus the torque due to 2. So I think that since 1 and friction are at the axis, these go to 0 at the axis. Anytime there's a force acting on the axis, there's no torque from it. So gravity is going to be the negative mg times w. And then this one will be h. And it'll be N2 is pushing this way. So N2 is the only force. I think it's going to rotate it counterclockwise. So that'll be a positive. So that's actually okay. Plus N2 times H. So that's 0. So what that means is that N2 is equal to mgw over H. And that's positive. So what I've just shown here is that you do need, it can't be 0 to have a normal force on the bottom, or else the gravity would rotate the whole thing clockwise. So I'm just saying it's got to push from the bottom. And that's why it has to pull at the top. N1 is equal to negative mgw over H. And what that means is that this is actually to the left. So I've drawn it to the right, but that was wrong. And that's another thing with static friction or normal force. I guess tension, you always kind of know the direction that pulls in on the string, but with static friction and normal force, sometimes you don't know the direction, although a normal force should be away. In this case, it's a sticky thing on the top, or else it doesn't work. Any questions about that? Does that look okay to you guys? Okay. We'll do chapter 11 one? No, sorry, chapter 10. When is this one? Something disappeared on me here. Chapter. Oh, I did one. Which one should we do first? Let's do this one. Let's actually do a chapter 10 one first, and then we'll do a chapter. So this one, you attach a 1.6 kilogram object to a spring, and you pull it down from, so I think this is a hanging spring, I guess. So I think it looks like here's the spring with no mass on it. And then what happens is you hang a mass off of it. And this is like the mass equilibrium. So the spring is no longer in equilibrium, but now the mass is in equilibrium. So if you pull it down or push it up, it's going to oscillate around the mass equilibrium. So then you pull it down to 0.13 centimeters below that, and you release it from rest. So V initial equals 0, and then it's going to go kind of like this. So like this would be the 0 point right there. So this is x equals 0. And I guess it was released from below. So what I'm going to do, because what I want to do is I want to use x equals a times cosine of 2 pi over t times t. Do you remember that is equation 10.2? That'll work if we set define plus to be down. Plus x is down. Then it works, right? And so a is going to be the 0.13 meters. You release it from rest, and then it should shake around with this simple harmonic motion. SHM. That's my basic idea. And again, there's Hooke's law, which is what drives all this. Fx is equal to negative k times x. So it makes sense, right? Hold it up, that pushes it down. Anyway, that's the idea there. You've got the mass is equal to 1.6 kilograms, and k is equal to 250. You're asked where it is at 0.2 seconds. So, but you're going to need the period from this. So let's look at. I found it as equation 10.7, which was t is equal to 2 pi times the square root of m over k. So 2 times 3.14159 times the square root of 1.6 divided by 250. If it's all in SI units, I get t is equal to 0.5027 seconds. And then now we'll just use x equals a times cosine 2 pi over t times t. But you got to remember, have your calculator set into radians mode if you're going to type this cosine. So make sure your calculator, because if you do degrees, this isn't going to work, is in radians mode for this. So x is equal to 0.13 times the cosine of 2 times 3.14159 times 0.2 seconds divided by 0.5 seconds. And when I did that, I got negative 0.1042. So that means that's meters, I think. That's the distance, that's the position at that particular time. So I guess, and that's how far it is away from equilibrium. So it's 0.10 meters from equilibrium is the 0. So this equation x equals a times cosine 2 pi t over t. It doesn't come up that often. Actually use it that much. So that's why I think it's safest to set your calculator in read mode most of the time, but it does come up with a switch. Or you could, I guess, convert this to degrees before you type in there, multiplied by 180 and divided by pi. That's a work. Okay. Okay, this one, and again, I'm going to post all this in the class 36. Yes. Well, so this particular equation assumes that whatever is in this is in radians. It's not degrees yet.
Is that radian, or is it just?
Well, it's definitely this equation. There might be other equations. No, I see a pi in there. No, it's called the radians. Look through the book. Okay. That's the only one I can really think of where it comes up. Okay. All right. So this one is this is a problem set one from that last problem set, but people were not getting it. So it's simpler than you think. How you get the 7 centimeters? I'll show you what's going on. So they're saying that this guitar has a fundamental frequency, and this is actually how guitar strings do work, is that the main sound you hear is the fundamental frequency. So L is equal to 0.69 meters, and the whole thing shakes up and down. And so we're assuming a standing wave and what's called the first harmonic. So the equation here is for F1. F1 is equal to 294 hertz. And then what you're going to do is you're going to push down your finger with like a fret. A fret reduces the effective length by forcing a node that's not at the end of the string. So the string is clamped down at both ends, but if you push down with your finger, it forces a node and reduces the effective length of the thing. Effective length. So L goes down. And you have an equation somewhere, which is F1 is equal to V over 2L. But you don't know V. So normally you would find V by having the tension and the mass density of the string, but you're not given any of those things. But I think it's okay because you just assume those are fixed. So recall, it's something like V is equal to the square root of F over mu, which is fixed. If you push your finger down on the string, it won't change the tension very much. And it also definitely doesn't change the mass density of the string. So that's okay. So we'll just assume that V is constant. And actually, we can figure it out. So we don't know this stuff, but what we can do is say that V is equal to F1, like original, times 2 times L, the little originals here. You know what I mean? You know that's 294 hertz, and oopsie, sorry. Slow down here. And you know that it's a length of 0.69, so I can actually figure out the speed if I want. And then I can say F1 is equal to V over 2 L nu or something. So L nu is equal to 2 times 294 times 0.69 divided by 2 times 330 hertz. That's what you're trying to get. You're trying to raise the frequency. So somehow you get 0. So now that's not the right answer, as it turns out. You got it right, but I think it was asking how far from the end do you press your finger, so you have to minus up the 69. So this is 61.5 centimeters from the left end. So the fret is 69 minus 61.5 equals 7.5 centimeters from the right end. Oh, wow, there's somebody on Zoom asking. Why can't we just, oh yeah, that's a really good question, Lydia. So it's a string. So it's a bit confusing, right? Because you hear the sound, so there's some sound. But what's happening is you have a standing wave on a string, which is your basic standing wave. And then it also sends a traveling wave of sound out into the air that reaches your ears. So it's a different thing. So when you're solving all the standing wave frequency stuff, you got to use this V for the string. Really good question. That's smart. Okay. Yes, question. Yeah, I think all acoustic instruments are based on standing waves. Either the two main classes are going to be, wind instruments and string instruments. And so string instruments are standing waves on a string. That's what's actually amplifying the sound, really. And especially in a wind instrument, you are creating some initial energy or initial vibrations with some sort of initial oscillator, like a reed in a wind instrument, or even in a flute, you're kind of blowing over an open hole, or in a brass instrument, you're kind of vibrating your lips against the mouthpiece. But what amplifies a particular frequency so that everyone else can hear it is a standing wave of sound in the pipe of the wind instrument. So it's a little more complicated with wind instruments, but and I guess also even in a string instrument, you got to pluck it or bow it or something like that to give it that initial energy. But then there's a standing wave that gets set up in the string that gives you that nice sound. And then also you've got the box of the instrument. If you have a violin or something, there's that wooden box, which then further amplifies the sound that you hear with standing waves of sound that are in sort of 2D standing waves of sound inside the box. So it's a whole thing. On Zoom here. Okay, good. Yeah, so this was just, I want to talk about banked curves a little bit again. So once again, anytime you are staying on a curved path, there is a radial component to your acceleration, which is v squared over r. And in uniform circular motion, this is a constant number because v is constant. But if you have tangential acceleration as well, so for example, you're on this curve and you're speeding up or slowing down, that's okay. This equation still applies. You still have v squared over r, but the v changes with time. And now you have two components to your acceleration. So your actual acceleration vector will be on a diagonal, which is, if you're speeding up, will be not towards the center. But you'll have a radial component, which is v squared over r, and you'll have a tangential component, which depends on how hard you're stepping on the axis. Or on brakes, and backwards. So that's like the top view. And then there's this idea of where does that force come from? And it comes from static friction, because you're rolling without slipping. And static friction, I have a little animation here. It produces a force parallel to the surface called the static friction force. So right now there's zero static friction because there's not much going on, but I don't know if you saw it. When you step down more with your foot, these things kind of lock in, and you get a increased normal force. The shapes lock together better, and there's more contact. So the maximum static friction force increases. So that's where this Fs max is proportional somehow to the normal force. These friction equations have always been a bit mysterious to me. I never know really where they come from, but I do know where they come from. They just come from these tables that you look up. The engineers measure it somewhere, and it just turns out that things seem to be pretty proportional to normal force. But what you also see is that they'll have different coefficients of friction for different ranges of normal forces as well. So like it's just approximate, right? And it doesn't always exactly work. but they're handy equations. And okay, so what I'm working up to is this static friction. So static friction is a self-adjusting force. And you had something like this on your problem set before, but this came up on a past test. So a car drives on a banked highway curve at some speed v. The curve has radius r and is banked at an angle theta. So you see the top view there, and then you also see the rear view. And there's that banking angle theta. On this, so if you're going to draw a force diagram from the rear view, well, I would, if you draw it here, and maybe this is where the surface is, then there's a normal force acting up, and there's mg acting down. It says, in what direction do you draw the static friction force? So, recall, the main thing you have to know here is that there's something called a frictionless banked curve problem. And we worked through this, any weather or something like that. And what happens there is you define y to be up, and then r to be directly towards the left in this, because that's towards the center of the circular path that the car is driving on. You believe me? You're looking from behind. He's not accelerating down the hill. He's accelerating directly towards the center of that big horizontal circle. So what that means is that this is r. You have a sub r is equal to v squared over r, and you have a sub y equals 0. So that's good. So then you kind of have to sum all this stuff up. You get that n is now the diagonal force. There's ny and there's nr, and gravity is not on the diagonal. So this is different than when you have, for example, just an incline and something sliding on the incline, and then you have the acceleration parallel to the incline. You should tilt your axes. Don't tilt your axes in the bank curve problem. What do? You do that. How do we do this? Oh yeah. So you say that the sum of the forces in the y direction equals 0, and you get that n cosine theta is equal to minus mg, right? Is 0. So you get that n equals mg over cos theta. Surprisingly, that's not mg cos theta. And then you also have that the sum of the forces in the r direction is m times v squared over r. And the only thing pointing in the r direction is just n sine theta. And so what you can do is plug this into that, and you get mv squared over r. This is where the m's cancel. Mg over cos theta times sine theta is equal to mv squared over r. And this gives you your critical speed. Somehow it all solves out. I end up with v critical is equal to the square root of g times r times tan theta, because tan is sine over cos. Okay, where am I going with this? What I'm trying to say is that if v equals v critical, then the static friction force equals 0. You don't need any static friction. That would be like D. But if V is greater than V critical, then what'll happen is it'll kind of want to slip off the hill, like off the curve into the ditch. And so you need some static friction acting down the hill to keep it on the road. So Fs is to the left. And I guess also down, because it has to be parallel to the surface, right? So like that. And then also if V is less than the V critical, then I think that Fs is to the right. Because what you've got then is it's going slow. So like it could even be stopped, I guess. It wants to slide now down the hill, and so you need some static friction to keep it on the hill. And like that. So the answer is sort of crazy, doesn't it? And I guess the moral of the story here is that, you know, what these physics tests, I mean, some of it is going to be fairly straightforward. Did you kind of learn the basics? You kind of remember physics? But I also want to test your reasoning ability and your conceptual understanding of what is happening here. And use kind of your common sense and sort of global knowledge. So this is a hard question, actually, but it's not unlike a question that I might ask you on set. So this is why I say you got to have a good night's sleep the night before. Is that your most valuable resource is going to be your brain. You got to think about these things and think, you know, what would Harlow say? Like, what is this going? What's really going on here? And so this is the idea: is that you can't know which direction the static friction force is unless you know the speed. How are you doing?
Yeah.
You're comfortable? Okay. Yes, question. Yeah. You don't have to need V. Make sense? Yes. You just need these. If you know V, then you're good. Okay, you know these. Yeah, that's exactly it. Yeah. So specifically, you need V. Need V. That's okay. He wanders. He's finding vending machines. Okay. All right, time's it. All right, so let's do, I want to do a chapter 9 rotational inertia because people are asking me, remember that door that was either like a wooden door or the door frame? So let's do something that's like that came up before. Basic idea is that for a discrete system of masses, the rotational inertia is the sum of m's, all the m's times all the r squareds. And that crazy table, this one, or something like that, this was on some previous exam, so it must have been a different textbook, but same basic idea. These are shapes that are made up of lots of tiny particles. And what somebody did, somebody who knows calculus, they went through and added up all those little mr squareds and figured out that, like for this spherical shell, if you take the entire mass of the spherical shell and the radius of the spherical shell, and then multiply by 2/3, you get it right. So it's all, they all have these fractions except for the hoop. The hoop is just actually mr squared because in that case, all the particles are at the same distance, roughly, from that rotation axis. So you don't need a fraction. You're just adding up all the masses and multiplying them all times the same thing, which is r squared. And so you just get the sum of all the masses times r squared. And it's just the total mass times r squared. So you don't need a fraction for the hoop, but everything else has this crazy fraction in front of it. And I will give you this, either this table or I'll just tell you in the question. So I'm not giving you this table. I'm going to tell you in the question the specific equation that you need. If you need it. There will be at least one chapter 9 question, maybe 2. All right. So what are we doing here? We're doing this. A steel square frame, 1 meter times 1 meter in size, and it weighs 4 kilograms, et cetera, is rotated about an axis which passes through its center and goes through its plane, like that, right? Around the central vertical axis. And it's just asking what's I. So basic idea, I could call it M1, M2, they're all the same, M3 and M4. So they're all equal to was 1, and it adds up to 4 kilograms, and they're all that same length. So for 1 and 3, I think they're going to be the same, but what you're going to do is look at your table at this point. So it's you guys see it? For the ones that are spinning at the top and bottom, I think it's like a thin rod around about center. So it's 12. 1/12 of m times L squared. And so m and I guess L is 1 meter. So it's just a 12th. And then for 2 and 4, that is not on the table. I don't know what it is, but luckily this is like that door thing, is that I think all the particles are at the same distance from the rotation axis, so you can just use their total mass times L over 2. L over 2. So I'm just going to say I2 equals I4 is equal to the mass times 0.5 squared. And that actually just ends up being 0.5 squared. So you just get I is equal to I1 plus I3 plus I2 plus I4. Somehow when I summed it up, I got 2 times 1 over 12 plus 2 times 0.5 squared. I got 0.67. Hopefully that's right. Something like that. Okay. I'm going to come back to another chapter 9 in a minute, but I wanted to do a center of mass one, which we'll do this one next. You see it? So this is asking for the center of mass of this triangular shape. And it's not going to look all that fun, but I'll show you how I did it. First of all, it says that the 60 centimeter length of uniform wire, 60 gram mass. So 60 centimeter length, I just wanted to check that that's actually true. So it doesn't, what they're saying is that the perimeter is 60. 10 plus 26 plus 24 equals 60. So that's right, actually. So what that means is that it's, and that's also so it's mu, I guess, is 1 gram per centimeter. Makes sense? Because it's 60 grams, m equals 60 grams. And it's 60 centimeters, so that kind of makes some sense. It's physics 131. You want to come in? You can stand there too, but there's lots of room. So yeah, okay, stand is all good too. I like standing. Okay, so what I'm going to do is treat the object as 3 bars, and we know where the centers of those bars are, so we'll just add them up. Because the bars themselves are pretty simple. And then we can just use like X center of mass is equal to M1. We'll call this M1. We'll call this M2 down here, the easy ones. M3 is the diagonal one, which is a little hard. But X center of mass will be M1 X1 plus M2 X2 plus M3 X3 divided by M1 plus M2 plus M3. So treat as 3 bars. So M1 is equal to 10 grams, M2 is equal to 24 grams, and M3 is the diagonal one, is 26 grams. Like I say, you guys are welcome to come on in if you want to. Come on in. And X1 and Y1 are pretty easy. It's right there. So X is 0 and Y is 5 centimeters, right? And X2 and Y2 is going to be here. And that's actually 12 centimeters and 0. So the tricky one, which actually turned out to not be that tricky, is after I thought about it for a really long time. You'll never guess where this is. I think it's similar triangles. So like definitely it's got to be 13 centimeters to go from here to here and 13 over here. But if you think of it, so where am I here? This triangle and this bigger triangle are kind of similar. So if this is like, what's this, 12? And this is 5. Anyway, I think this is 12. This is 5 and 5. I don't know. There's some sort of similar triangle that, to me, I don't know why this wasn't obvious. They're just in the middle. 12 centimeters and 5 centimeters. I thought I was going to have to do some trig or something like that, but after staring at it for a long time, I think we're okay. Just halfway points. And now it's just, you can type it in, right? So you've got 0 plus 24 times 12 plus 26 times 12. And then divided by 60 grams, and I got 10. And then y center of mass is equal to, same thing, m1 y1 plus m2 y2 plus m3 y3, all divided by the total mass. So that one was 10 times 5 plus 0 plus 26 times 5, I guess, and divided by 60, and I got 3. So if you do x center of mass, y center of mass, you get 10 and 3. Okay. Right. Good. So any object that has an obvious center, you can treat it as, I guess, a point mass at that center. So that's the big concept here. And it seems to come up a lot in these tests. So be ready to do that. Okay, this one you're not going to like, but again, it's one of these sort of thinking ones. Below is a position time graph, and it's really hard to read it here, but what I see is that this is 0, 20, 40, 80, etc. The motion sensor is set so that its samples per second is 40. So these are samples. It's the way it got displayed in your practicals, I think. And then it wasn't until you clicked the Analyze tab that it converted it all to seconds. But it asks you to determine the value of the spring constant of the spring with a estimate of the uncertainty. So it's 40 samples per second. What I could do to find the period is sort of count the number of oscillations and divide, take time, divide by the number of oscillations. So what I think I'll do, if this is one oscillation, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I think the more you take, the kind of more accurate you'll be, right? 11, so this is 11. The 11th oscillation comes at sort of like 305, maybe plus or minus 5. This is like an estimate. I'm estimating the uncertainty here because the tick-D marks on this graph seem to be about 5 samples. So kind of roughly. That's going to give us our percent. So this is 11 oscillations. And so the way I did it is I said that T is equal to 305 plus or minus 5 divided by 11. Also times 40 samples per second in order to convert it to seconds. Samples per second on the bottom. I've got samples. So the samples will cancel and the second will come up to the top and you'll have seconds. So I got T is equal to 0.693 seconds, where I've just used the 305. And I'm going to come back and do the uncertainties at the end because I know the percent uncertainty. But let's just work through what the actual values are. Maybe they're waiting for the next thing. Okay, we'll use equation 10.7, which is that T is equal to 2 pi times the square root of m over k, and solve it out. You're trying to find k, right? So you can divide and square both sides. Those are 4 pi squared is equal to m over k. And then you get k is equal to the mass times 4 pi squared divided by t squared. So I plug all that stuff in. The mass is 0.2006. So this actually has its own percent uncertainty, but we'll get back to that later. Times 4 times pi squared divided by 0.693 squared. Anyway, I got k is equal to 16.49. Okay, newtons per meter. Now the issue here is the uncertainties. So what we can do is we can say that we can check here percent uncertainty is 5/305. This one is equal to 1.6. This is actually just from my estimate of that 5. It's 1.6%. The other input value was this one over here, which is 0.1/200.6. Whenever you use that scale, you get like 0.05% uncertainty. So this right here is the weakest link by far. And so I think it's pretty simple, just times it by. So the uncertainty in K is 16.49 times 0.016, which is 0.26. So anyway, what I would write is that K is equal to, I'll just round this to the 10th column. I might as well round this to the 10th column too. So I would display it as 16.5 plus or minus 0.3 newtons per meter. That was a really hard one, but not insanely difficult. And there will be something to do with uncertainties on your week. I'm going to post all this stuff, by the way, of course. Oh, there's Lydia. A second. I've muted her. How'd you ask? Yeah, that's a good question. What I did is that's the key, isn't it? I could have said 3 and I would have got something a bit different. But it is really just an estimate, Lydia. So if you had written down 3 instead of 5, I mean, it's not 0. Like it's 305, so I'm just sort of using common sense that I don't think it's less than 300, probably. And I don't think it was more than 310. So part of when you're working in the lab is you have to make estimates like this. I guess I used the ticky marks on the graph. They were fine. That's one way. But there is no magic answer to that. And if you had used plus or minus 3, I think it would have been perfectly fine. You would have got a different answer. You would have gotten 16.5 plus or minus 0.2 or something, but it would have also been equally correct. Okay. Okay. Once again, I think that's where I'm going to leave it. But the final exam is December 16th. It's on Saturday. This is the official room assignments. I think somebody may have on Acorn sort of mixed up the names a little bit, but like I say, it's just these 8 rooms anyway, so they're all Physics 131, so not to panic. If you go to the wrong room, I'm going to try my best to make sure you can stay there. But best thing, and then Allah has assured me, go to this short one that's here. The best thing, and then you'll know for sure that you see. I guess worst case scenario is that too many people go to the wrong room and then there's not enough seats. I'm also fighting very hard with OFR, the Office of Faculty Registrar, to fix the Acorn schedule as soon as possible. They're working on it. I don't know what the hell the issue is over there, but somebody can't remember their password or something. It's just not. It's the stupidest thing in the world. But just trust SharePoint for now. I'm sure it's correct. And I'll see you guys on Saturday. And if not, I'll see you in my office hours next week. I'll be around in room 127. That's posted. Okay, thanks very much.